A dead star hangs in the dark with a surface no wider than a city, yet heavy enough to bend the path of light around itself. Nothing there resembles a world. The ground, if that word can still be used, is pressed almost perfectly flat by gravity, while beneath it, atoms have already lost their old names. Electrons have been driven into protons. Nuclei have swollen with neutrons. Deeper still, matter may be waiting in shapes no laboratory has ever held for long. Before the descent begins, thank you for resting here for a while. If this quiet science journey helps you relax, learn, or drift closer to sleep, please subscribe to the channel, leave a like, and share it with someone who enjoys the darker corners of the universe. And softly, before the star draws the story inward, write where you are listening from, and what time it is where the room around you has gone dim. Let the lights lower a little. Let the fan, the blanket, or the small sounds nearby settle into the background. There is no need to remember every number or every particle. The important thing is the slow movement downward, layer by layer, from the faint X-ray glow at the surface to the hidden core where matter is pressed. Close to the edge of becoming something else, the star will not be opened all at once. It will be approached the way distant light is approached, patiently, through the signs it leaves behind. The first view is not inside the core. It is above the star, where light still escapes, where pulses cross space, and where a collapsed remnant keeps one last boundary against the dark. Around that boundary, gravity has almost finished its work, but not completely. That unfinished collapse is where the story begins. At the heart of the Crab Nebula, the old star has not entirely vanished. Its outer layers have been scattered into space, drawn into filaments of gas that glow under the energy of the remnant left behind. The cloud is wide and slow, a torn shape still expanding through the dark. Near its center, where the original core collapsed, a compact object turns inside the remains of such a death. The object is small enough to fit inside the width of a large city. That smallness is misleading. More mass than the sun can be packed into a sphere only a few tens of kilometers across. And the result is not a planet, not a burning star, and not yet a black hole. It is a neutron star, a body so compressed that the ordinary language of matter begins to lose its grip. Surface, weight, hardness, and height still have meaning there, but each word has been forced into a new scale. The surface is where the story first becomes visible. It is the last material boundary before the hidden interior begins, and it is also the proof that collapse has not finished its work. A black hole offers no solid face to the outside universe. A neutron star still does. However thin, hot, and crushed that boundary may be, light can leave it. Radiation can carry information away. Matter has not crossed the final line. Gravity rules that surface with a severity unlike anything on Earth. A stone dropped from a small height would not simply fall. It would strike with energies that belong more to nuclear physics than to ordinary impact. The pull is so strong that mountains cannot rise in any familiar way. Rock on Earth can hold ridges, slopes, cliffs, and broken ranges. A neutron star crust, even if far stronger than ordinary rock, is pressed almost flat by the weight beneath it. A mountain there may be smaller than a grain of sand, yet still carry a mass that would matter to astronomy. So the surface can be smooth and strained at the same time. Smooth because gravity allows almost no relief. Strained because the crust below is not passive. It can hold magnetic stress, store heat, crack in small rearrangements, and anchor fields that reach far beyond the star itself. The calm outline seen from a distance is not a sign of ease. It is the shape of matter being disciplined by gravity every instant. Some neutron stars reveal that discipline through pulses. Their magnetic poles do not always line up with their rotation, and charged particles move along the field lines near those poles. Radiation escapes in narrow beams. As the star spins, those beams sweep through space. If one crosses Earth, a radio telescope records a pulse, then another, with a rhythm that can remain steady for years. Nature has made a clock from the corpse of a star. That clock is not gentle inside. A neutron star can turn many times each second. Some rotate hundreds of times each second, carrying the angular momentum of a large stellar core squeezed into a body, only city-sized. The same motion shapes the region around the star, where magnetic fields and charged particles form a restless magnetosphere. Energy leaks away through radiation and particle winds. Very slowly, the dead star loses spin, like a wound spring unwinding across astronomical time. The most magnetic neutron stars carry the surface story further. In magnetars, the magnetic field is not only something outside the star. It reaches into the crust and presses on it. A starquake in such a place is not an earthquake moved to another world. It is a fracture in dense nuclear matter, under gravity, so strong that vertical motion has almost no freedom. The release may appear to telescopes as a flare of X-rays or gamma rays, but the origin lies in a crust, trying to answer a magnetic field that has become part of the star's internal stress. Above the crust, the atmosphere may be extremely shallow. On a neutron star, the outer gas may be only a thin skin, sorted by gravity so quickly that lighter elements float above heavier ones. It can be far hotter than any flame, and still too compressed to resemble air in the ordinary sense. Radiation leaving this layer carries signs of temperature, composition, magnetic field, and gravity, all blended together before the signal reaches space. Light itself does not escape casually. The star's gravity stretches its wavelength as it climbs outward, shifting the radiation toward lower energy. This gravitational redshift is one of the ways the surface marks its own compactness on the light it releases. The light has had to climb from a deep well in space-time. It leaves changed. Its path is changed too. Around a neutron star, space is curved strongly enough that light from parts of the far side can bend into view. The surface is not transparent, but the geometry around it allows more of the star to be seen than a normal sphere would show. A distant observer may receive radiation from regions that would otherwise be hidden behind the limb. The star is small, but its gravity makes the visible surface larger than simple intuition expects. This bending matters, because the surface is read rather than touched. No instrument descends through the atmosphere. No sample of crust is brought back. Observatories gather pulses, crays, bursts, cooling curves, and small changes in timing. From those signals, astronomers estimate mass, radius, temperature, magnetic fields, and the pressure of matter that cannot be reached directly. A normal living star shines because fusion in its interior creates energy that eventually works its way outward. A neutron star is different. It is the aftermath of fusion's failure. Its surface emission can come from leftover heat, magnetic disturbance, accreted material, or rotational energy being drained away. The glow is not a simple lamp connected to a simple furnace. It is a set of traces from an object whose deepest support remains buried. The support is the real subject. The surface only announces that support exists. Somewhere below the thin atmosphere and the rigid crust, matter still pushes back against gravity, not by ordinary heat alone, not by chemical bonds, not by the pressure that holds a main sequence star open. The resistance comes from quantum rules and nuclear forces, from particles crowded so closely that empty space inside matter has nearly disappeared. The visible boundary is only the upper edge of that deeper contest. This is why a neutron star is more than a dense sphere. It is a stopped collapse. Gravity has already crushed the core of a massive star past ordinary atoms. Electrons have been driven into conditions where chemistry no longer describes the material. Protons and electrons have been forced together, leaving behind a body dominated by neutrons, with smaller populations of charged particles still needed for balance. The matter has moved beyond the common states, taught by everyday experience. It is not solid, liquid gas, or plasma in any simple sense, and yet the star has not become a black hole. A material boundary still stands where, under slightly different conditions, an event horizon might have formed. Light still escapes from the outside layers, pulses still cross space, heat still fades into X-rays. The star continues to answer the universe with signals, faint and altered though they may be. The edge between neutron star and black hole is also an edge between two kinds of knowledge. As long as the neutron star has a surface, matter can still speak. It can speak through brightness, timing, cooling, flares, and gravitational distortion. Once collapse passes behind a horizon, the interior becomes sealed away, leaving far fewer clues about what the matter had become before it disappeared. The surface of a neutron star is the first sign that the final silence has not arrived. It is thin, compact, and bent by gravity. It is almost flat and still under strain. It carries heat from below, shapes light on the way out, and holds the marks of rotation and magnetism. It is the visible face of a deeper resistance. Beneath that face, pressure rises with startling speed. A short distance downward is not a small change in such an object. It is a passage into another regime of matter, where atoms have already failed, and nuclei are being pressed toward forms that cannot exist in ordinary space. The descent cannot begin with the core. It begins here, at the last surface, where the dead star still has an outside, and where the fact of that outside tells the whole story has not yet fallen into darkness. Long before a neutron star becomes a small dark point inside the remains of an explosion, it begins as something much easier to recognize. A living star hangs in space, bright enough to warm planets, broad enough to seem almost permanent, and steady enough that its danger is hidden by its patience. From far away, the sun looks calm. Its light arrives softly after crossing the distance to Earth, filtered by air, scattered by clouds, broken into morning and evening. Nothing in that familiar glow suggests a body held open by force. Inside the sun, gravity is always pulling inward. It does not wait for the star to age. It does not gather itself for a later moment. Every layer of plasma presses on the layers beneath it, and the weight grows heavier toward the center. If nothing answered that pull, the star would contract. Its own mass would draw it smaller, hotter, denser, and more tightly bound. A star survives because something inside it pushes back. That balance has a quiet name: hydrostatic equilibrium. The phrase sounds still, almost sleepy, but it describes a continuous contest between inward gravity and outward pressure. In a stable star, neither side wins completely. Gravity holds the star together. Pressure keeps it from falling inward. The star is not motionless in the deeper sense. It is maintained by equality, by forces so large that their balance appears calm only because they are matched. The pressure in a main sequence star comes mostly from hot plasma and from the energy released in nuclear fusion. Plasma is matter in which electrons are no longer bound neatly to atomic nuclei. It is a charged fluid, shaped by temperature, pressure, radiation, magnetic fields, and motion. In the core of the Sun, hydrogen nuclei move in such heat and density that they sometimes come close enough for the strong nuclear force to join them. The result is helium, with a small amount of mass transformed into energy. That energy becomes part of the outward pressure, holding the star open. Fusion is not an easy flame. It is not a simple burning surface. Hydrogen nuclei carry positive charge, and positive charges repel one another. They resist being pushed close together. The solar core has to supply heat, density, and time. And even then, the process depends on quantum behavior that allows particles to cross barriers that ordinary motion alone would not overcome. The Sun shines because gravity compresses its center until matter reaches the narrow conditions where nuclear physics can release energy. The balance is self-correcting in a slow and powerful way. If the core becomes slightly hotter, fusion becomes more active. More energy appears, pressure rises, and the star expands a little. Expansion cools the core, and the reaction rate settles. If the core cools too much, pressure weakens, gravity squeezes the center tighter, temperature rises, and fusion strengthens again. The star breathes without lungs. It adjusts because the same gravity that threatens it also helps create the conditions that save it. This is the first form of resistance in the life of a star: heat and fusion answer. Gravity, the material, remains extended because its particles move, collide, radiate, and transform in ways that supply pressure. The star is not solid. It has no surface like a planet. Its visible edge is only the layer where the gas becomes transparent enough for light to escape. Beneath that apparent boundary, the whole object is a deep arrangement of pressure, mass, and energy. The phrase equation of state belongs here, before it belongs to neutron stars. In simple terms, it means the rule that tells how matter responds when it is heated, squeezed, or allowed to expand. For ordinary gas, that rule links pressure, temperature, and density in ways that can be tested in a laboratory. For a star, the same idea becomes larger and more demanding. It tells how the material inside each layer pushes back against the weight above it. In the Sun, the answer is known with unusual clarity because the star is close enough to study in more than one way. Light from the surface reveals temperature and composition. Small vibrations across the solar body reveal interior structure, like waves moving through a bell that is too large to hear. Neutrinos born in the core pass outward almost untouched, carrying evidence from the fusion region long before ordinary light can reach the surface. Together, those signals show a star whose internal pressure keeps pace with gravity across billions of years. A neutron star is still far away in this story. But the question has already appeared. How does matter answer pressure? At low density, ordinary gas can expand. At higher temperature, plasma can push outward. In the core of a living star, fusion can supply energy. Each answer works only under certain conditions. No form of support is universal. Gravity waits beneath all of them. As a star ages, the answer begins to change. Hydrogen in the core is gradually converted into helium. The core does not run empty in a sudden moment, but its original fuel becomes less able to support the same balance. The center contracts. Around it, shells of hydrogen may continue to burn, and the outer layers respond by expanding. The star becomes larger and cooler at the surface, even while its inner regions grow denser and hotter. A red giant is not a relaxed star. It is a star whose inner balance has been rearranged. For stars like the Sun, The next stages lead toward a white dwarf, not directly toward a neutron star. The outer layers drift away over time, and the exposed core remains behind. That path matters because it shows that gravity does not always find the same ending. A star's fate depends on mass. A smaller star never builds enough central pressure to make the deepest collapse. A larger star can continue beyond helium, building carbon, oxygen, neon, silicon, and heavier nuclei in a sequence of shorter and more demanding burning stages. In massive stars, the interior becomes layered. Shells burn different fuels at different depths, with each layer formed from the ashes of an earlier reaction. Hydrogen gives way to helium. Helium gives way to carbon and oxygen. Deeper inside, heavier reactions appear if the star has enough mass to reach them. The timescales shrink as the star approaches its final stages. What once lasted millions of years can give way to phases that are brief by stellar standards, as the core searches for one more reaction that can hold gravity back. The sequence cannot continue forever. Iron sits near the end of the useful road. Its nucleus is bound so tightly that fusing it does not release energy in the way earlier reactions do. It costs energy for a massive stellar core that changes everything. The star has spent its life using nuclear reactions to answer gravity, and now the inner material can no longer provide a profitable answer through fusion. The old support has reached its limit. The surface may still look like a star for a short time. Light may still leave the outer layers. The enormous body may still appear whole from the outside. But deep inside, the central bargain has failed. Gravity is still pulling inward, as it always has. The pressure that once matched it is no longer enough. The core begins to contract more severely, and as it does, the kind of matter inside it changes. This is the pattern that leads toward every compact remnant. Matter survives under gravity only by finding a form of pressure that can hold, in a living star, heat and fusion hold. In a white dwarf, another kind of support will appear after fusion has mostly faded. In a neutron star, an even deeper rule must take over after ordinary atoms have been broken apart. Each stage reveals a new defense, only when the previous defense fails. The living star therefore matters to the story of impossible matter, because it provides the first, gentlest version of the same contest. Gravity presses, matter answers. For most of a star's life, the answer is bright, warm, and familiar from a distance. The answer is sunlight, starlight, the long patience of fusion, held inside a sphere of plasma. But the light is not permanent. It is a phase of resistance, and resistance has limits. When those limits arrive in a massive star, gravity does not become a new force. It simply continues the work it had been doing all along. The difference is that the old pressure can no longer keep pace. The star that once shone by balancing inward pull with outward energy now begins to reveal the deeper layers of physics hidden beneath its fire. The next form of support is quieter. It does not come from fusion. It comes from the refusal of particles to be crowded into the same quantum state, and it first appears in the dense, fading remains of stars that do not quite become neutron stars. Sirius B is almost lost beside the bright star that shares its name. The larger companion shines with a clean white light, familiar to the night sky, and easy for the eye to imagine as a star. The smaller object beside it is harder to hold in thought. It is dimmer, compact, and old, a stellar core left behind after the outer layers of its former life drifted away into space. It no longer burns hydrogen in the way a living star does. It glows because it still remembers heat. A white dwarf looks like a gentler remnant, only when compared with what comes later. It is roughly the size of a planet rather than the size of a city. Its gravity is strong, its density far beyond rock, and its surface light comes from stored heat slowly, leaking into space. The star is dead, in the sense that fusion no longer holds it open. Still, it does not collapse. Something remains inside it, answering gravity after the fire has almost gone. That answer is not ordinary pressure from heat. A white dwarf can keep cooling for ages, and cooling alone does not make it shrink into nothing. The support comes from the quantum behavior of electrons, particles so light that they provide little of the remnant's mass, yet powerful enough in their crowded state to help hold up a body as massive as a star. The old flame is gone, a rule remains. In ordinary matter, electrons live around atomic nuclei. Their arrangements shape chemistry, color, hardness, and the difference between one material and another. They make stone feel solid, metal conduct electricity, and atoms keep their identities. Inside a white dwarf, the old atomic pattern has been broken. The nuclei are packed into a dense structure, while the electrons are no longer tied to neat shells around single atoms. They form a compressed sea running through the whole remnant. The rule that matters is the Pauli exclusion principle. Electrons belong to a class of particles called fermions, and fermions cannot all occupy the exact same quantum state. In a quiet atom, this rule helps create the layered structure of electron shells. In a dying star's core, it becomes something far larger. It becomes pressure. As gravity squeezes the white dwarf, electrons are forced into a smaller volume. The lowest available quantum states fill first. Once they are occupied, the next electrons cannot simply join them. They must take higher energy states. Not because the material is hot in the ordinary sense, but because the rules of identity leave no lower place open. Compression creates resistance. The remnant pushes back because sameness is forbidden. This resistance is called electron degeneracy pressure. The name sounds cold and technical, but the image is simple enough. Matter has been crowded until the electrons have almost no ordinary room left. Gravity tries to make the remnant smaller. The electrons answer by occupying higher and higher energy states. Their motion and allowed quantum positions become the architecture holding the white dwarf apart. It is not like air inside a balloon. Air pressure weakens as the gas cools because the particles move more slowly. Degenerate pressure can remain even when the remnant loses heat, because it is rooted in quantum exclusion rather than warmth. A white dwarf can fade, becoming dimmer over immense stretches of time, while still remaining supported. Its survival is not a memory of fire. It is a memory of order at the smallest scale. This is one of the quiet reversals hidden in stellar death. A star begins by holding itself open with fusion, with heat, radiation, and plasma motion. After that support fails in a smaller star, the remaining core is held open by particles refusing to be placed into the same state. The support of a body, the size of Earth, is written into rules that first revealed themselves in atoms. The white dwarf is therefore a bridge. It is stranger than a normal star, but not yet as severe as a neutron star. Its matter is dense enough that chemistry has lost its usual freedom, yet not dense enough for protons and electrons to be forced together in large numbers. Nuclei still remain as nuclei. Electrons still remain as electrons. The parts of ordinary matter have been stripped of their familiar arrangement, but they have not yet been driven into the deeper collapse that makes neutrons dominant. That bridge has a limit. Electron degeneracy pressure is strong, but it is not without end. As more mass is placed into a white dwarf, gravity grows stronger. The electrons must occupy higher energy states to resist the added compression. The object becomes smaller as it becomes heavier, which feels backwards compared with ordinary things. A pile of stones grows larger when more stones are added. A degenerate star can shrink when mass increases, because added gravity tightens the entire quantum structure. There is a final mass where this support can no longer keep up. It is known as the Chandrasekhar limit, named for Subrahmanyan Chandrasekhar, who showed how relativity changes the behavior of electrons in the most massive white dwarfs. Near this boundary, the electrons are driven so hard that their speeds approach the range where Einstein's physics must be included. Adding mass no longer strengthens the support in the needed way. The safety net has reached its edge. The value is roughly 1.4 times the mass of the Sun, though the exact behavior depends on composition and details of the remnant. Below that range, a white dwarf can remain stable, cooling very slowly as its light fades into the future. Above it, the object cannot remain a white dwarf. Gravity has found the condition under which electron degeneracy pressure no longer provides a stable answer. In a binary system, a white dwarf may approach that boundary by drawing matter from a companion star. From outside, the process can appear gradual, a stream of gas crossing space and settling onto a compact remnant. Inside, the consequence is more severe. The added mass presses the electron sea closer to its limit. Once the balance fails, the white dwarf may ignite runaway nuclear burning and destroy itself as a type Ia supernova, or in other circumstances move toward collapse into a still denser state. The exact ending depends on the system, but the lesson is the same. A form of pressure can work beautifully inside its allowed range and fail completely beyond it. Gravity does not need to become stronger in kind. It only needs enough mass to ask more than the available support can answer. The white dwarf survives because of electrons, but electrons are not the final defense of matter. This prepares the path toward neutron stars with unusual clarity. In a white dwarf, the star has already lost ordinary fusion support. It has already become a compact remnant. It has already shown that quantum mechanics can hold up a stellar corpse, but its particles remain separated in a way that still resembles the ingredients of atoms. The nuclei carry most of the mass. The electrons carry much of the pressure. The division can last only while the mass remains low enough. When a massive stellar core exceeds the white dwarf path, the same rule cannot save it. The electrons are pushed so high in energy, and the density becomes so severe that another transformation begins. Electrons are driven into protons. Charged particles are forced to merge into neutrons. The electron sea that once held a white dwarf open begins to disappear. The first quantum safety net tears. There is no anger in that failure. There is only sequence. Fusion holds first. Electron degeneracy holds later if the remnant is light enough. When the mass is too large, matter is pushed through the next threshold, and the answer must come from a deeper level. The star is no longer asking electrons to keep nuclei apart. It is asking whether neutrons themselves can resist being crowded beyond recognition. The white dwarf remains important because it shows that collapse can be stopped by a rule rather than by heat. It shows that microscopic identity can decide the fate of a macroscopic object. A particle too small to see, obeying a law too quiet to picture directly, can help hold up a dead star for longer than planets have existed. But the rule has an edge. Beyond that edge, the remnant cannot stay planetary in size. It cannot keep the old separation between electron and nucleus. Gravity presses inward again, deeper than the white dwarf can bear. toward the place where atoms lose their last familiar pieces, and the core begins to make neutrons in overwhelming numbers. The next stop is not a cooler ember. It is the collapse that stops only after matter has been remade. The birth of a neutron star begins before the supernova is seen. From the outside, a massive star may still appear whole, its outer layers wide and bright, its surface giving no simple warning of the failure taking place far below. Deep in the center, the long sequence of nuclear burning has reached a condition that cannot provide the old answer. The core has become heavy with iron group material, and iron does not return useful energy when fusion tries to push it further. The star has arrived at the end of the road that living stars use to hold themselves open. Gravity is still there, unchanged in its patience. It has pulled inward for the entire life of the star. For a long time, fusion answered. Hydrogen, helium, carbon, oxygen, and heavier stages each gave the core another way to resist. Near the end, those stages came faster, one after another, like the fading breaths of a structure running out of choices. The final core can no longer bargain with gravity through light and heat in the same way. Pressure weakens. The center begins to fall. The collapse is not the falling of ordinary material into an empty space. It is a change of identity. Matter is being forced through thresholds, where the familiar pieces of atoms can no longer remain separate. Electrons, which helped hold up white dwarfs through degeneracy pressure, are now crowded into a density where their safety net is no longer enough. The core is too massive. The quantum room that allowed electrons to resist compression cannot carry the weight that has gathered above it. As the density rises, electrons are driven into protons. The process is called electron capture. A proton and an electron become a neutron, and a neutrino is released. One by one, the charged architecture of matter is being erased. The atom, already stripped and pressured, far beyond chemical life, loses the separation that once gave it form. The core is no longer a place where electrons circle nuclei. It is becoming a place where neutrons appear in overwhelming numbers. This transformation deepens the collapse. Electrons had been part of the pressure support. As they are captured, that support is removed. At the same time, neutrinos flood the core. In most settings, neutrinos are nearly untouchable messengers, able to pass through planets and stars with little interruption. Inside the collapsing core, even they begin to meet a wall of density. For a short time, the material becomes so packed that neutrinos can be trapped, scattered, and delayed inside matter that would be transparent to them almost anywhere else. The scale has shifted. A density that belongs inside an atomic nucleus is being extended across a stellar core. What is normally confined to a microscopic region becomes the condition of a body kilometers wide. This is one of the quiet shocks of neutron star birth. The universe takes the inner density of nuclei and asks it to support something large enough to be astronomical. The old gap between particle physics and stellar structure disappears. Still the center falls. Nuclei are pushed closer together until the empty spaces that once separated them become less meaningful. The distinction between one nucleus and the next begins to blur. Neutrons no longer belong only inside nuclear boundaries. Matter is approaching nuclear density, and at that depth a different kind of resistance begins to rise. Neutrons are fermions, as electrons are. They also obey the Pauli exclusion principle, which means they cannot all be forced into the same quantum state. When the collapsing core becomes dense enough, neutron degeneracy pressure begins to matter. Nuclear forces also enter the contest. At very short distances, Neutrons and protons do not behave like soft grains being poured into a pit. Their interactions can become strongly resistant. The inward fall meets a barrier made from quantum exclusion and the close-range behavior of nuclear matter. The central part of the core stiffens. Collapse slows, then halts, then rebounds slightly. The language can make this sound like a simple bounce. But the event is not simple. The material has fallen inward at enormous speed, changing composition as it goes. When the inner core suddenly resists, the outer core is still falling. A shock wave forms at the boundary where these motions meet. For a moment, the star has created the outline of an explosion from its own failed center. That shock cannot easily escape on its own. As it pushes outward, it loses energy by breaking apart heavy nuclei and fighting through infalling material. The early shock stalls. A supernova is not just a rebounding ball of gas. It is a layered process involving neutrino transport, turbulence, rotation, magnetic fields, and the changing stiffness of dense matter. Neutrinos are likely part of the rescue. A fraction of the vast neutrino energy, leaving the newborn compact core, can be absorbed behind the stalled shock, heating the material there and helping drive the explosion outward. The visible supernova is the part the galaxy notices. The outer layers brighten and expand, carrying gas enriched by the star's long nuclear life and by the conditions of the explosion. Elements are scattered into interstellar space. A growing remnant begins to take shape, a cloud that may shine for centuries or longer as shock waves move through it. The old star is opened and dispersed. At the center, the quieter result is more severe. The collapsed core has become a neutron star. If it has not crossed the final line into a black hole, it is no longer supported by fusion. It is not supported by electron degeneracy in the white dwarf sense. The main resistance now comes from neutron-rich matter, nuclear interactions, and the equation of state that decides how pressure rises as density increases. The remnant is small, hot, and still changing. Its first moments are not peaceful. The newborn neutron star is born with enormous heat and trapped energy. Neutrinos pour outward as the remnant cools. The crust is not yet the cold, rigid shell it may later become. Material from the explosion may fall back toward the compact object, adding mass or altering the outer layers. Rotation has been compressed from the old stellar core into a much smaller body, so the remnant can spin rapidly. Magnetic fields have been drawn inward and strengthened by collapse. A star that once spread across millions of kilometers leaves behind an object only a few tens of kilometers wide. This shrinkage concentrates more than matter. It concentrates rotation, magnetic flux, and the unresolved memory of the explosion. The new neutron star is an aftermath still settling into itself. Its surface, atmosphere, crust, and core will continue to cool and rearrange as the remnant ages. The name neutron star is useful, but it is not complete. Neutrons dominate the story because electron capture has remade the core. Yet the star is not a pure ball of neutrons. Protons remain in smaller numbers. Electrons remain to help maintain charge balance. Muons may appear deeper inside when conditions allow them. At still greater densities, other forms of matter may become possible. Even at birth, the object has layers and uncertainties. Its name points to the main transformation, not to a finished inventory. The important fact is that collapse has stopped. Matter has found another way to resist. Fusion held the living star. Electron degeneracy could hold a white dwarf if the mass stayed low enough. In this deeper remnant, neutron degeneracy and nuclear forces become the next defense. They do not guarantee safety forever. A more massive core may pass beyond them and form a black hole. But in this case, for this remnant, the inward fall has been interrupted. The interruption is what makes the neutron star so valuable. It is a boundary object, suspended between an ordinary stellar corpse and a horizon from which no surface light can escape. It carries the record of a supernova and the evidence of matter under pressure that no laboratory can hold for long. The expanding nebula tells the story of what was thrown away. The compact star tells the story of what did not keep falling. After the light of the explosion spreads outward, the descent into the remnant begins in a quieter way. The first surface cools. The atmosphere thins into a compressed skin. Beneath it, the outer layers settle into a crust that is not rock, not metal, and not any ordinary solid. The star has been born by collapse, but its strangest matter is now waiting below the heat, arranged in the first rigid boundary of the dead core. A neutron star does not need a deep atmosphere to separate itself from space. The outer gas can be thinner than the height of a building, pressed close to the surface by gravity, that allows nothing to float freely for long. Hydrogen or helium may form the upper skin if those light elements are present, not because the place is gentle, but because gravity sorts matter with severe efficiency. Heavier nuclei sink. Lighter particles remain above. Even this first layer is already an arrangement made by force. The word atmosphere brings the wrong memory at first. It suggests wind, clouds, weather, and a gradual fading into sky. Around a neutron star, the atmosphere is a compressed veil, hot enough to glow in shrays, and shallow enough that a person could imagine crossing it in a few steps, if such a step could exist there. There is no open blue height. There is only a thin region where radiation is shaped before it escapes. That shaping matters. Light leaving the atmosphere carries signs of temperature, composition, magnetic field, and surface gravity. It does not bring those signs cleanly. The same pulse of ray light may depend on how hot a region is, what the surface is made of, how strongly the magnetic field guides charged particles, and how much gravity bends the path outward. The atmosphere becomes a translator, but not a simple one. Beneath that veil, the star becomes a crust. The word crust must be used carefully. On Earth, crust means rock, mineral plate, fracture, and a slow-moving planet beneath it. On a neutron star, the crust is not built from stone. It is a lattice of atomic nuclei, immersed in a sea of electrons, held together under pressure that has already stripped matter away from ordinary chemistry. There are no familiar minerals. There is no granite, no basalt, no soil. At the upper edge of the crust, nuclei can still be recognized as nuclei. They are often far richer in neutrons than the stable atoms found on Earth. Around them, electrons no longer sit in neat shells that create chemical bonds. They are squeezed into a degenerate sea, moving through the lattice as part of a dense charged background. The crust may behave like a solid in some ways, but it is not a solid in the everyday sense. It is a frozen arrangement of nuclei and electrons under a gravitational weight that never relaxes. The descent through the outer crust is not a descent through layers of rock. It is a descent through pressure. Each small step inward brings the nuclei closer together. The electrons become more energetic because they are confined to less space, and that rising energy changes which nuclei can survive. Some electrons are captured by protons inside nuclei, turning them into neutrons. The nuclei grow more neutron-rich as the depth increases, held in states that would not last long in ordinary laboratories. This is one reason the crust is difficult to understand. On Earth, Nuclear physicists can create rare isotopes for brief moments and measure their behavior before they decay. In a neutron star, pressure changes the rules of endurance. It can allow exotic nuclei to remain in place as part of a global shell, not because they are stable in isolation, but because the star gives them no ordinary environment in which to fall apart. The crust is therefore known through experiments, theory, and the signals the star sends back. Those signals are subtle. A hot region on the surface may rotate into view, brighten the X-ray pulse, then pass away again. If the star is compact, gravity bends light from around its side and softens the rise and fall of the pulse. If the magnetic field is strong, heat may flow more easily in one direction than another, making the surface uneven. A distant telescope receives a pattern. Beneath that pattern lies a crust whose structure cannot be seen directly. The crust stores heat. That quiet fact matters after an outburst, especially in systems where matter from a companion star falls onto the neutron star and heats the outer layers. When the outburst fades, the crust cools back toward balance with the deeper interior. Astronomers watch the X-ray brightness decline over months or years, and from that fading light, they infer how well the crust conducts heat, how much energy it's stored, and how its layers are arranged. The cooling surface becomes a delayed echo from below. The crust also guides electric currents and anchors magnetic fields. In ordinary stars, magnetic fields can move through plasma in broad, flowing ways. In a neutron star crust, the dense solid shell can hold and distort magnetic stresses. In magnetars, where the magnetic field is stronger than in ordinary pulsars, those stresses may become large enough to strain the crust. The surface then carries tension that began as magnetic energy and became mechanical stress. When the crust shifts, the star can flare. The comparison to an earthquake is useful only for a moment, then it begins to fail. Earthquakes move through rock plates under planetary gravity. A magnetar flare involves a rigid nuclear crust, a magnetic field tied to the star, and gravity so strong that the surface has almost no freedom to rise. The motion may be small in shape and large in consequence. Radiation bursts outward, even without a flare. The crust may hold tiny distortions. Gravity tries to smooth every raised place, pressing the surface almost flat. Still, the crust has strength. If it can support a slight asymmetry on a rotating star, that uneven mass may create gravitational waves, faint ripples moving through space-time. The mountain would not need to be tall. On a neutron star, a height too small to notice by human standards could involve enough mass to matter. The question is not whether the mountain looks large. The question is whether the crust can bear it. This turns the crust into a bridge between nuclear physics and astronomy. The strength of dense matter decides the shape of a star. The shape of the star may decide whether ripples leave it. A microscopic arrangement of nuclei and electrons becomes part of a signal that a future detector might search for across space. The path from particle behavior to gravitational waves remains connected. The crust is thin compared with the whole object. That thinness can mislead. A layer only a small fraction of the star's radius may contain more mass than familiar worlds. A depth that seems slight in kilometers can cross major changes in density, composition, and particle behavior. In ordinary places, small distances often mean small differences. Here, a narrow shell can decide how heat escapes, how magnetic stress breaks, how rotation changes, and how surface light is shaped. The surface that first appeared as a boundary now becomes a working part of the star. It is not only the outside of the object. It is a thermal blanket, a magnetic anchor, a mechanical shell, and a filter for radiation. It receives heat from below. It absorbs matter from above. If the star has a companion, it carries the marks of gravity and rotation. It is the part of the neutron star most visible to telescopes, and still every signal must be interpreted with care. Deeper down, the nuclei become more crowded. The electron sea becomes more energetic. The neutron excess grows. The old separation between particles inside nuclei and particles outside them begins to weaken. The crust has already removed the ordinary meaning of atoms. It has replaced chemistry with pressure, electron shells with a degenerate sea, minerals with a nuclear lattice. Yet, this is only the outer crust. The next boundary is quieter in name and deeper in meaning. It is the place where neutrons begin to leave nuclei behind. There, matter enters a mixed state. Some neutrons remain bound in nuclear clusters. Others move through the spaces between them, no longer confined to a single nucleus. The crust is still a crust, but it is becoming less like a lattice of separate pieces and more like a crowded region where solid structure and flowing neutron matter overlap. The star is preparing to change its identity again. The first solid boundary of the neutron star has done its work. It has shown that a surface can be thin and still carry immense meaning. It has shown that a crust can be almost flat and still strained, narrow and still heavy, hidden and still readable in light. Beneath it, the descent continues toward the neutron drip region, where the particles that gave the star its name begin to move freely through the dark interior. The descent reaches a boundary that has no familiar surface. There is no line drawn through the crust, no sudden wall, no color change that a distant telescope could see. The material simply becomes dense enough that the old arrangement can no longer hold every neutron inside every nucleus. Pressure has been rising from the surface downward, folding matter into smaller possibilities. Now it reaches the point where neutrons begin to leave the nuclei that once contained them. The name is neutron drip. It sounds almost soft, as though something were slowly falling through a quiet ceiling. The reality is stranger and more severe. A neutron does not drip like water. It escapes confinement because the nuclei have become so neutron-rich, and the pressure around them has grown so high that adding more neutrons inside the same nuclear boundary no longer remains the lowest energy arrangement. Some neutrons are pushed into the space between the clusters. The crust enters a mixed state. Above this depth, the outer crust is made of neutron-rich nuclei sitting in a degenerate sea of electrons. Below it, the inner crust begins. The nuclei are still there, but they are no longer alone. Free neutrons move around them, filling the spaces between nuclear clusters like a silent background fluid. Electrons remain present as well, maintaining charge balance and carrying their own pressure through the lattice. The result is neither ordinary solid nor ordinary liquid. It is a layered quantum material, built under gravity, and held in place by density. This is the first time the name neutron star becomes physically visible in the descent. At the surface, the star was known by gravity, light bending, heat, and magnetic stress. In the outer crust, atoms had already been stripped of their normal form. But at neutron drip, the particles that define the star begin to appear outside nuclei. The neutron is no longer hidden only inside compact clusters. It becomes part of the wider material. The transition does not happen because the star is hot in the ordinary sense. It happens because pressure changes the energy balance of matter. A nucleus on Earth with too many neutrons would often decay quickly, returning toward a more stable arrangement. Inside the crust of a neutron star, the environment is different. Electrons are crowded. Gravity is relentless. The density is high enough that the usual pathways of nuclear stability are altered. The star permits nuclei to become more neutron-rich than they could remain in open space, until even that arrangement can no longer contain all the neutrons. Free does not mean free in the human sense. These neutrons are not leaving the star. They are not moving into empty space. They are free only from individual nuclei, still trapped inside the gravitational field of the remnant, and still shaped by the surrounding matter. They move through a narrow region of the crust, where solid nuclear clusters and a neutron sea coexist. Their freedom is local, and it belongs entirely to the prison around them. That local freedom may change how the star rotates. In the inner crust, many of the free neutrons are expected to form a superfluid when the star cools enough. A superfluid is a state of matter that can flow without ordinary viscosity. It does not behave like water, oil, or molten rock. Its motion is governed by quantum rules. Rotation inside such a fluid is not spread smoothly through the material. It can be carried by tiny quantized vortices, thin lines of rotational motion threaded through the neutron fluid. A neutron star is slowly losing rotational energy as it radiates. Its outer crust and magnetic field break over time. The star turns a little more slowly across the years. The superfluid component below the crust may not slow in exactly the same way. Some vortices can become pinned to the crustal lattice or to irregular structures deeper down. While the crust gradually loses spin, the superfluid can keep a hidden store of angular momentum. The difference builds quietly. Then, sometimes, a pulsar glitches. The steady rhythm suddenly shifts. The star spins slightly faster than expected, as if something inside it has handed motion back to the crust. The change can be small, but in a pulsar timed across years, small changes matter. One leading picture is that vortices in the inner crust unpin and move, transferring angular momentum from the superfluid to the solid outer layers. A signal measured by a radio telescope may therefore carry the trace of neutron motion beneath the crust. Nothing about this has to be forced into drama. The value is in the quiet connection. A clock in space misses its expected beat. The reason may lie in a hidden fluid made of neutrons, flowing under a nuclear crust, far below a surface whose mountains cannot rise. The observation is delicate. The interpretation remains active research, but the link between a timing irregularity and the inner crust is one of the most useful ways the star lets its buried layers speak. The neutron drip region also affects heat. A neutron star cools from the inside outward, and the crust can delay, store, and redirect that heat. The presence of free neutrons changes the heat capacity of the material, meaning how much energy it can hold as its temperature changes. Superfluidity changes this further, because paired neutrons do not carry heat in the same way as unpaired particles. A layer that seems thin by distance can influence how the surface temperature fades after an outburst. The same region can shape how vibrations and stresses travel. The crust is solid enough to bear strain, while the neutron component can move differently beneath it. The two do not always act as a single simple body. They exchange motion, heat, and stress through microscopic interactions. This makes the inner crust a place of coupling. It joins the visible surface to the hidden interior, the rigid shell to the fluid below, the pulse that reaches Earth to the quantum behavior of particles under pressure. The nuclei themselves continue to change with depth. They are pressed closer together, and their neutron richness grows. The free neutron sea becomes denser. The boundary between a nuclear cluster and its surroundings becomes less clean. Matter is no longer arranged as separate islands in a simple background. The islands are beginning to feel the presence of one another through the surrounding neutron, fluid, and electron sea. Shape will soon become part of the answer. Before that happens, the neutron drip layer gives the descent a quieter lesson. A neutron star is not uniform. It is not a single ball of compressed neutrons. It is built from transitions, each one taking away another familiar form of matter. The atmosphere removed the idea of air. The outer crust removed the idea of chemistry. Neutron drip removes the idea that neutrons must remain locked inside nuclei. The star changes not by crossing a visible doorway, but by forcing matter into new rules as pressure rises. There is a kind of stillness in this. The inner crust may sit beneath the surface for thousands or millions of years, cooling, adjusting, and turning with the star. Its free neutrons may flow in a way ordinary fluids cannot. Its vortices may wait, pinned in place, until the slow breaking of the crust makes their arrangement unstable. Its heat may leak upward with a timing that reveals the properties of dense matter. None of it is directly seen. All of it may matter. A small change in wording can hide a large change in physics here. Bound neutrons belong to a particular nucleus, sharing its identity and its limits. Dripped neutrons belong to the crust as a whole. They turn the inner crust into a shared system, rather than a collection of separate nuclear objects. From this point downward, matter is less like an assembly of pieces, and more like a continuous negotiation between clusters, fluids, and fields. The descent now moves deeper, toward a region where even the nuclear clusters begin to lose their roundness. The pressure has already loosened neutrons from their nuclei. It will next begin to sculpt the nuclei themselves, stretching and flattening them into shapes that belong to no ordinary material. In the dark, below the neutron drip layer, matter prepares to become geometry. Below the neutron drip region, the inner crust grows stranger without becoming sudden. There is still no sharp doorway where one kind of matter ends and another begins. Pressure rises. Nuclei crowd closer together, and the free neutron sea becomes denser around them. The old picture of round nuclear clusters, sitting apart from one another, begins to fail. Matter has not yet become the more uniform fluid expected in the core, but it no longer prefers the simple shapes that ordinary nuclei keep in the open world. A nucleus is not a little stone. It is a bound collection of protons and neutrons held together by the strong nuclear force, with protons also pushing against one another through electric repulsion. In an ordinary atom, these forces settle into compact nuclear shapes, while electrons arrange themselves outside and chemistry begins around them. Inside the inner crust, chemistry is already gone. The electrons are a dense background. Neutrons move between clusters. The pressure is high enough that the boundary of each nucleus becomes less private. This is where nuclear pasta may appear. The name is almost too playful for a place like this, but it gives a useful image to matter that cannot be seen directly. In models of the inner crust, nuclear material may stretch into long rods, flatten into broad sheets, open into tubes, or form bubbles where dense matter and void-like regions trade places. The comparison to pasta does not make the physics gentle. It only gives the mind a shape to hold, while the real material exists under gravity that would crush ordinary solids out of recognition. The structures arise because no single force is in charge alone. The strong nuclear force favors keeping protons and neutrons close. The electric repulsion between protons resists packing too much positive charge into one region. The surrounding free neutrons change the energy of each arrangement. Electrons spread through the material and help maintain charge balance. Gravity supplies the pressure that makes the compromise unavoidable. Matter answers by changing shape. Higher in the inner crust, round clusters may still be favored. Deeper down, rods may reduce the energy of the system. Below that, sheets may become more stable, as if nuclear matter were being pressed into broad layers. At still greater depth, the pattern may invert, with tubes or bubbles appearing inside a denser background. These are not clean geological beds. Stacked like rock strata, they are possible low-energy arrangements of dense nuclear matter, and a real neutron star may carry them imperfectly. That imperfection matters. Simple diagrams can make nuclear pasta look orderly, almost like a set of shapes arranged for inspection. A real crust has a history. It was born hot, cooled through neutrino emission, may have been strained by magnetic fields, may have received fallback material after the supernova, and may have been shaken by glitches or flares. Its pasta layer may contain defects, mixed phases, tangled regions, and irregular boundaries. It may be less like a neat drawing, and more like a frozen landscape at nuclear scale. The scale is difficult to feel. The layer may be thin, compared with the whole neutron star. It may occupy only a small part of the inner crust. Yet, density changes the meaning of thinness. A narrow shell can contain more mass than familiar worlds. A small depth can carry enough material to influence heat, rotation, magnetic stress, and the way the surface cools after disturbance. In neutron star matter, size and importance no longer walk together. If nuclear pasta exists, it may be among the strongest materials known. Strength here means resistance to deformation before breaking, not usefulness in any ordinary environment. Steel is strong because metallic bonds hold atoms together under strain. Diamond is hard because carbon atoms form a rigid lattice. Nuclear pasta is held by nuclear forces under compression so severe that its predicted breaking strain can be far beyond ordinary matter. It is strong because the star has made it captive. That last point is important. Nuclear pasta could not be scooped out, cooled, and set on a table, removed from the pressure that forms it. The arrangement would not remain what it was. Its strength belongs to the conditions that imprison it. The neutron star creates the material by pressing nuclear matter into shapes it would not choose in empty space. The same pressure that makes it possible also makes it unreachable. Pasta layer may influence how heat escapes. After an outburst, the crust can be heated, and then slowly cool back toward the temperature of the deeper interior. X-ray telescopes watch the fading surface light as the crust relaxes. The timing of that fading depends on how easily heat moves through the layers below. Nuclear pasta could scatter particles, redirect heat, or slow the flow of energy. A small change in dense nuclear geometry can become a change in a light curve measured across space. Neutrinos may also carry information through this region. These light particles drain energy from young and hot neutron stars, and their movement depends on what they encounter. Structures in the crust can scatter neutrinos or change how efficiently energy escapes. The effect is subtle, but subtle effects matter in an object where no direct sample can be taken. A telescope sees cooling. The interpretation reaches downward into rods and sheets of nuclear matter. Rotation brings another connection. In the inner crust, free neutrons may form a superfluid, and that superfluid can rotate through quantized vortices. Those vortices may become pinned to the crustal lattice or to pasta structures. As the outer star gradually slows, the pinned superfluid can keep a slightly different rotation. Stress builds between the flowing component and the solid shell. When vortices unpin, angular momentum may move suddenly into the crust, producing a pulsar glitch. A small change in timing may have passed through a hidden forest of nuclear shapes. The exact mechanism remains unsettled. Some models give the pasta layer a strong role in vortex pinning. Others place more weight on different parts of the inner crust, or on the coupling between the crust and the deeper core. The honest picture is not a solved machine. With every gear labeled, it is a set of linked clues. Pulsar timing, crust cooling, nuclear theory, and dense matter simulations all point toward the inner crust as an active participant rather than a passive shell. There may also be a gravitational consequence. If the crust and pasta layers are strong enough, they may support tiny asymmetries on a rotating neutron star. A raised region would not need to be tall. Under such gravity, even a very small distortion could represent a large mass imbalance. A spinning asymmetry can emit gravitational waves, faint ripples in space-time. The strongest material in the star might therefore announce itself not by being touched or seen, but by allowing the remnant to remain slightly on as it turns. That possibility is quiet but powerful. A microscopic structure in the inner crust could decide whether a macroscopic star is smooth enough to hide from gravitational wave detectors, or uneven enough to whisper into them. The chain is long. Nuclear force shapes matter. Shaped matter gives strength. Strength allows asymmetry. Asymmetry disturbs space-time. The signal, if it exists, would be small. The idea is still worth carrying because it shows how deep the connection runs. Nuclear pasta sits at a threshold. It is not ordinary crust anymore, but it is not the core. It is not made of isolated nuclei in a simple electron sea. But it is not yet uniform neutron-rich fluid. It is matter caught between identities, forced to become geometry, before it becomes something smoother that, in between nature, is what gives the layer its scientific weight. The descent through a neutron star is often imagined as a movement into greater density alone. The pasta layer shows that density is only part of the story. Matter does not merely become more packed, it reorganizes. Atoms disappear. Nuclei grow neutron-heavy, neutrons drip out. Nuclear clusters stretch, flatten, and invert. Each step takes away a familiar form and replaces it with a stranger arrangement that can exist only because gravity has left no gentle option. Below the pasta, the clustered shapes are expected to dissolve. The crust gives way to the core, where neutrons dominate a dense fluid, and pressure becomes the central question. The next layer will be less visual. There may be no rods, sheets, or bubbles to picture. Instead, there is a hidden rule, the equation of state, deciding how strongly matter pushes back. As gravity tries to compress it further, the geometry fades, and the deeper resistance begins. Beneath the pasta layers, the neutron star enters a region where shape gives way to response. The rods and sheets of the inner crust are expected to dissolve into something smoother, a dense core, where matter is no longer arranged as separate nuclear clusters. The descent has passed through atmosphere, crust, neutron drip, and distorted nuclear geometry. Now the star becomes less visual. The deeper question is not what shape matter takes, but how strongly it pushes back. This is the domain of the equation of state. The phrase sounds like a piece of mathematics kept far from the surface of a star, but its meaning is direct. It is the rule that links pressure, density, and energy inside matter. In a room of ordinary air, such a rule would describe how the air warms, expands, or grows denser when compressed. In a neutron star core, the same idea survives, but the material has moved far beyond familiar gas. Heat is no longer the main support. Quantum rules and nuclear forces carry the weight. The core is often imagined as a sea of neutrons. That image is useful only as a beginning. Neutrons dominate much of the matter, but the core is not pure. Protons remain in smaller numbers. Electrons remain as well, helping preserve electrical balance. At greater density, muons may appear, heavier cousins of electrons that become possible when the energy of the electron sea rises high enough. The name neutron star hides a continuing negotiation among particles. That negotiation has to maintain balance. If too many neutrons convert into protons, electrons, and other particles, or if too many particles convert back into neutrons, the composition shifts until the reactions settle into equilibrium. This condition, called beta equilibrium, helps determine the mixture inside the core. Charge neutrality must also be preserved, so the positive charge of protons is balanced by negative particles, such as electrons and muons. The core is dense, but it is not careless. Every particle species appears, only if the local pressure and energy allow it. Neutrons still obey the Pauli exclusion principle. They are fermions, so they cannot all be crowded into the same quantum state. This gives neutron matter a form of degeneracy pressure, deeper than the electron pressure that holds white dwarfs open. Yet degeneracy alone is not the full answer. At nuclear densities, particles also feel the strong nuclear force. At some distances, that force binds nucleons together. At very short distances, the interactions can resist further compression. The pressure of the core comes from both exclusion and interaction, from identity and force, working in the same dark region. The stiffness of the equation of state tells how quickly pressure rises when density increases. If pressure rises strongly, the matter is called stiff. A stiff core resists compression, allowing a neutron star of a given mass to have a larger radius. If pressure rises more weakly, the matter is called soft. A soft core yields more readily, making the star smaller and bringing it closer to collapse for the same mass. These words are only shorthand. The star is not made of rubber or clay. It is made of particles packed so closely that their allowed states and forces decide the size of the entire remnant. A small change in the core can become a large change at the surface. If the pressure at high density is slightly different, the radius of the star may shift by kilometers. A few kilometers sound modest beside ordinary astronomical distances, but for a neutron star they are large. The whole object is only the size of a city. A change of that scale alters how strongly light bends around the star, how hot regions appear as the surface rotates, and how the star deforms in a merger. The hidden pressure becomes visible through geometry. The difficulty is that the core cannot be sampled. No vessel can hold this matter. No instrument falls through the crust and sends back measurements. The equation of state is inferred from consequences. Astronomers weigh neutron stars in binary systems. They estimate radii from X-ray pulse patterns. They observe cooling surfaces. They read gravitational waves from mergers. Each method touches the hidden rule from a different side. Mass is the most direct demand. A measured neutron star above 2 solar masses means the equation of state must be stiff enough to hold that weight. If a model of dense matter collapses before reaching such a mass, it cannot describe the stars already observed. Heavy pulsars, therefore, act like silent judges. They remove soft models that fail the simple requirement of survival. Radius is harder, but it carries a different kind of clue. The X-ray instrument, nicer studies rotating neutron stars, whose surfaces have hot regions. As those regions move in and out of view, their brightness changes. Gravity bends the escaping light, so the pulse shape depends on how compact the star is. By modeling that bending, along with the hotspot arrangement and atmosphere, researchers estimate combinations of mass and radius. The answer is not read in one clean glance. It is extracted from light that has crossed curved space-time. The same compactness affects merger signals. When two neutron stars spiral together, each pulls the other out of shape. The amount of tidal deformation depends on the equation of state. A larger, stiffer star is easier to deform during the final orbit. A smaller, softer star resists deformation in a different way because its mass is packed closer inward. The gravitational wave pattern carries the imprint of this response. It is as if the stars reveal their internal compressibility by stretching under each other's gravity before contact. Cooling adds another clue, slower and dimmer. A neutron star is born extremely hot, then loses energy through photons from the surface and neutrinos from the interior. The speed of cooling depends on which reactions are possible in the core. Some neutrino processes drain heat gradually. Others can carry energy away much faster, but only if the particle mixture allows them. If a neutron star is colder than expected for its age, the core may be allowing a rapid cooling channel. The surface temperature becomes a faint record of reactions far below. Superfluidity changes the core further. At the temperatures of a mature neutron star, which remain enormous by human standards, but can be low compared with dense nuclear energy scales, neutrons may pair together and form a superfluid. Protons may form a superconducting state. These paired phases do not behave like ordinary fluids or ordinary conductors. They can alter heat capacity, neutrino emission, magnetic field behavior, and the coupling between the core and the crust. The core is not only dense, it may be quantum matter, extended across an astronomical body. This is why the equation of state is more than a pressure curve. It is tied to composition, cooling, rotation, magnetic behavior, and the maximum mass the star can support. It decides whether the core remains mostly nucleonic, made mainly of neutrons and protons, or whether higher densities open the door to other particles. It decides how close the star can come to the edge of black hole formation while still keeping a surface. The correct rule must pass through a narrow corridor. It has to be stiff enough to support the heaviest known neutron stars. It cannot be so stiff that ordinary neutron stars become too large for X-ray and gravitational wave observations. It has to allow cooling histories that match the temperatures seen in real objects. It has to produce merger deformability that fits the waves already detected. Dense matter is being constrained from many directions at once. This narrowing is slow. One observation rarely solves the core. A heavy pulsar may demand stiffness, but not identify the particles that create it. An X-ray radius may favor one family of models, while still allowing several others. A gravitational wave event may rule out stars that are too large, but leave room for hidden transitions at greater density. A cooling neutron star may suggest fast neutrino emission, but the exact process can remain uncertain. The answer arrives by convergence. That convergence gives the core its strange power. It is hidden yet not silent. Its pressure shapes the radius. Its composition shapes cooling. Its stiffness shapes tidal deformation. Its paired particles may shape timing and magnetic behavior. The core never appears directly. But every surface signal is carrying some part of its influence outward. The descent into the neutron star has now reached the rule beneath the layers. Above it, matter had shapes: a thin atmosphere, a nuclear crust, neutron drip, pasta structures. In the core, the shapes fade into a dense fluid whose deepest property is resistance. Gravity continues to press inward. Matter answers through exclusion, nuclear force, particle balance, and perhaps paired quantum states. The answer is incomplete, but it is no longer empty. It is written in mass, radius, cooling, and waves moving through spacetime. A neutron star can look quiet from far away, while forcing theory into a narrow place. It may appear as a point that pulses in radio light, turning with a rhythm so steady that years of observation can be stacked together like marks on a hidden clock. The pulse comes and goes. The star rotates. Its companion moves around it. From those motions, astronomers begin to weigh something no scale could ever hold. One of the most useful examples is the heavy pulsar, known as PSRJ 0740 plus 6620. It is not visually grand in the way a nebula is grand. It does not fill an image with color or spread itself across light years. Its importance comes from measurement. The timing of its radio pulses, shaped by the motion of a white dwarf companion, shows that the neutron star carries more than twice the mass of the Sun. That alone makes it a severe test for dense matter. But a neutron star that heavy sits close to the upper range of what compact matter can support. Gravity has gathered so much mass into such a small body that any soft interior would struggle. If the pressure inside the core rose too weakly with density, the star would become too compact or fail to remain stable at all. The pulse arriving at Earth is therefore more than a rhythm. It is evidence that the matter inside the star has not yielded. The surprise grows when radius enters the story. A simple expectation says that a heavier neutron star should be squeezed smaller. More mass means stronger inward gravity. If the core gives way easily, the radius should shrink. In degenerate objects, this expectation is not always simple, because mass and radius do not behave as they do for ordinary planets. Still, a very heavy neutron star, with a radius broadly similar to lighter neutron stars, creates pressure on the models. It suggests that the core is resisting compression strongly. The star does not need to be impossibly large to matter. It only needs to avoid becoming as small as some soft equations of state would predict. A few kilometers of radius can decide which theories survive. Around a neutron star, kilometers are not small details. The whole object may be only a few tens of kilometers across. A radius that remains large under heavy mass is a sign that the dense interior has found a stiff response. This is where mass and radius become a kind of language. Mass tells how hard gravity pulls. Radius tells how successfully matter has answered. When the two are measured together, the star becomes a pressure test. The core is hidden, but it has left its influence on the size of the surface. The surface bends light, light shapes the pulse, and the pulse returns to telescopes, carrying part of the interior's answer. The X-ray instrument NICER has been important in this work. It observes hot regions on neutron star surfaces as the stars rotate. These hot regions do not simply brighten and vanish in the way spots on an ordinary sphere would. Gravity near a neutron star bends the light so strongly that more of the surface can remain visible during rotation. The pulse is softened and reshaped by curved space-time. By modeling that shape, astronomers can estimate combinations of mass and radius. The process is careful and uncertain. In the honest way, the atmosphere matters. The size and location of the hot regions matter. The viewing angle matters. magnetic effects may matter. A radius is not taken from the sky, like a number written on a page. It is inferred from light that has been filtered through a hot surface and bent through a strong gravitational field. But even with those cautions, the broad message of a heavy star that does not shrink too far carries weight. Soft models of dense matter feel that weight first. A soft equation of state allows matter to compress more readily. It may happen if new particle states appear and give the core easier ways to lower its energy. Hyperons may appear. Quarks may become deconfined. Other phases may open. These possibilities are not forbidden, but if they soften the pressure too much, the star cannot carry the measured mass. The sky removes those versions. That is the discipline of a heavy pulsar. It does not say which particles are inside the core. It says which combinations fail. Any proposed interior must keep the star alive. A hyperon-rich core must include interactions strong enough to avoid collapse. A quark core must stiffen at high density, or remain limited to conditions that do not destroy support. A mostly neutron and proton core must produce enough repulsive pressure to explain the radius and mass together. Every option has to pay the same pressure bill. The phrase exotic matter can be misleading here. It can make the core sound more capable simply because it is stranger. The opposite may be true. New particles often make matter more compressible because they give the system new ways to rearrange itself. A strange ingredient can soften the star instead of strengthening it. The heavy pulsar is valuable because it keeps speculation from drifting too far. It asks for support, not decoration. This creates the hyperon puzzle and the quark matter puzzle. Dense matter theory may suggest that at high enough pressure, additional particles should appear. Observed neutron stars say that if those particles appear, they cannot weaken the core beyond survival. Both statements may be true only if the interactions among the new particles are repulsive enough, or if the transition occurs in a limited region, or if the new phase stiffens again at higher density. The answer remains unsettled, but the allowed space is smaller than it once was. There is also a larger population to consider. Other heavy pulsars push the lower bound on the maximum neutron star mass. Each one adds another weight that the equation of state must support. At the same time, gravitational wave observations from neutron star mergers prevent the matter from being too stiff at lower densities. If ordinary neutron stars were too large, they would deform too strongly before merging, leaving a tidal imprint larger than observations allow. The correct rule has to thread between the demands. It must be stiff enough to hold heavy pulsars. It must be soft enough, in the right density range, to avoid oversized stars. It may change behavior with depth. A core could remain ordinary nuclear matter in one region, soften through a phase transition, then stiffen again deeper down. Such a curve would be difficult to see directly. It would hide inside the mass, radius, cooling, and merger behavior of different stars. This is why one heavy pulsar can reshape the discussion without solving it. PSRJ 0740 plus 6620 is not an answer by itself, it is a boundary marker. It says that matter at high density must resist strongly enough to support more than 2 solar masses. If its radius remains on the larger side of current estimates, it says that this resistance cannot appear only at the last possible moment. The core must begin pushing back before the star becomes too compact. The image is quiet. A rotating object, a pulse, a companion star, a timing delay, an X-ray pattern. Nothing in the observation looks like the pressure of nuclear matter. Yet the chain is unbroken. The companion helps weigh the pulsar. The surface light helps estimate its size. The size and mass constrain the pressure. The pressure constrains the particles. A faint rhythm from space becomes a test of matter, crowded beyond ordinary nuclei. The star that would not shrink is therefore not strange, because it breaks physics. It is strange because it makes physics more exacting. It removes easy answers. It narrows the interior. It allows exotic matter only if exotic matter can still act with strength. It allows ordinary nuclear matter only if ordinary nuclear matter remains stiff enough under conditions no laboratory can keep. Beneath its surface, the same hidden contest continues. Gravity presses inward with the weight of more than 2 suns. Matter answers from a core that cannot be seen, a core that may be mostly neutrons and protons, or may contain deeper phases waiting beyond the limits of certainty. The pulse crosses space as a small repeated signal. Behind it is a star holding its radius against compression, and in that held size, the interior leaves one more clue. At the depths, where the core becomes most crowded, the neutron begins to look less like an ending, and more like a container. It is not a fundamental particle. Like the proton, it is made of quarks, smaller constituents bound by the strong force so tightly that they are not found alone in ordinary matter. A neutron contains 1 up quark and 2 down quarks. A proton contains 2 up quarks and 1 down quark. That small difference shapes the charge of nuclei, the architecture of atoms, and the matter that builds the familiar world. Inside a neutron star core, the familiar world is already gone. Atoms have lost their form. Nuclei have been pressed into neutron-rich clusters, then stretched into inner crust shapes, then dissolved into a dense fluid, deeper down. The neutron remains one of the last recognizable structures. It carries the memory of ordinary nuclear matter, even under conditions where that memory is nearly erased. At still higher density, even this may not be permanent. If neutrons are packed closely enough, their individual boundaries may begin to overlap. The star is no longer asking how neutrons push against one another as separate particles. It is asking whether the neutron itself can remain intact. In some models, the deep core may pass into quark matter, a state where quarks are no longer confined inside individual protons and neutrons, but move through a wider dense medium. The nucleon, which had seemed like the final piece, may open. This idea follows the inward logic of the descent. Each layer has taken away a familiar form. The atmosphere removed ordinary air. The crust removed chemistry. Neutron drip loosened particles from nuclei. Nuclear pasta removed the roundness of nuclear clusters. A quark core would take away the separate identity of the nucleons themselves. The pattern is severe, but it is not a story of chaos. It is matter seeking the lowest allowed state under pressure. Quark matter is not an easy answer. The strong force that confines quarks inside protons and neutrons is not a weak barrier waiting to be broken. The transition depends on density, energy, temperature, and the behavior of the strong interaction in a region that no laboratory can hold in the same long-lived way. Theory can describe possible phases. It cannot simply point to the center of a neutron star and declare which one nature has chosen. There is also the pressure problem. New forms of matter often give a dense system more ways to rearrange itself. That can lower the energy, but it can also soften the equation of state. A soft core yields more easily to gravity. It makes a star smaller and can reduce the maximum mass that remains stable. Heavy pulsars already exist, with masses above 2 suns. Any quark matter inside such stars must not make them collapse. It has to appear in a way that keeps enough pressure. Some models allow this. Quark matter may soften the core at first, then stiffen again at higher density because of repulsive interactions among quarks. Other models allow paired quark phases, sometimes called color superconducting phases, where color refers to the charge of the strong force rather than visible color. In such a state, quarks organize into paired patterns, changing the heat capacity, cooling behavior, and pressure of the core. These possibilities remain careful, constrained ideas. They are proposals that must survive mass, radius, cooling, and merger evidence. Hyperons bring another possible change. A hyperon is a baryon, a particle made of 3 quarks like a proton or neutron, but with at least one strange quark in its structure. Strange quarks are heavier than the up and down quarks that build ordinary matter. Hyperons can be produced in high-energy experiments, but they usually decay quickly, outside the special conditions that made them. Inside a neutron star core, the situation may be different. When the energy of crowded neutrons grows high enough, it may become favorable for some matter to transform into hyperons. At first, that sounds like a natural relief. If neutrons are forced into very high energy states, opening new particle states can let the system settle into a lower energy arrangement. But relief is not always support. If many hyperons appear, they often soften the equation of state. The star becomes more compressible. The maximum mass can fall below the heavy neutron stars already measured. The particle that seems reasonable in theory may make the star too weak in practice. This is the hyperon puzzle. It is not that hyperons are forbidden. It is that their appearance must be balanced by interactions strong enough to keep the core stiff. Without that extra resistance, the model conflicts with real stars. The sky gives a simple command to every hidden particle. Appear if the density allows it, but do not take away the pressure needed for the star to live. Strange matter takes the idea further. If strange quarks join up and down quarks in a dense stable mixture, the result could be strange quark matter. Some hypotheses suggest that, under enough pressure, such a mixture might be more stable than ordinary nuclear matter. In that case, a compact object could be a strange star, rather than a neutron star in the usual sense, with different surface behavior and a different relation between mass and radius. This remains unconfirmed. No strange star has been identified with confidence. The idea survives because some models of dense matter allow it, and because observations have not yet closed every path. But a strange star would have to imitate many neutron star signals, while differing in subtle ways. It would still need to match pulsar timing, thermal emission, bursts, gravitational wave deformability, and the existence of heavy compact stars. It cannot be accepted only because the name sounds deep. There is a stronger caution as well. If strange quark matter were absolutely stable under ordinary conditions, small fragments of it, sometimes called strangelets, have been imagined as seeds that could convert normal nuclear matter into the strange phase. This remains highly speculative, with no observational evidence that such fragments are moving through space and changing matter on contact. Any strange matter hypothesis has to respect the world already observed. The center of a neutron star therefore becomes a filter for speculation. It may contain mostly interacting neutrons and protons, with electrons and muons preserving balance. It may contain hyperons whose interactions are strong enough to avoid softening the core too far. It may contain a quark phase that stiffens again at high density. It may hide a transition between phases that changes the interior while leaving the surface outwardly similar. Each possibility is allowed only as far as the whole star remains consistent. The key word is consistent. A model cannot only explain one feature. It must support heavy pulsars. It must give radii that match ray measurements. It must produce cooling behavior that does not contradict. Observed temperatures, it must allow tidal deformability, compatible with gravitational wave signals. It must place any phase transition where the star can survive it. Dense matter theory and astronomy are not separate. Here they press on the same hidden core from different sides. This makes exotic matter less like a secret treasure and more like a narrow passage. A quark core may sound like the natural final layer, but it has to hold pressure. Hyperons may sound inevitable at high density, but they have to avoid breaking the star. Strange matter may offer another family of compact objects, but it has to leave signs that can be separated from ordinary neutron star behavior. Nothing is free in the core. The most honest image is not a finished diagram. It is a set of possible interiors standing behind the same surface. From outside, the star pulses, its light bends, its radius is measured with difficulty, its cooling continues. Its merger with another neutron star may one day reveal how easily it deforms. Beneath those signals, the deepest matter may still be nucleonic, or it may have passed into a state where the neutron has opened. For now, the core keeps its silence. It does not show quarks directly. It does not label hyperons in the light leaving the surface. It does not announce strange matter by name. It allows only consequences to escape. The star remains a compact body, holding itself above collapse, and every proposed ingredient must help explain how that is possible. Gravity presses inward. The deepest particles answer, whatever they are. The next clue may come not from naming the matter, but from watching how the star cools as that hidden matter quietly carries heat away. A neutron star is born with heat that no surface can keep forever. In the first moments after collapse, the remnant is not the cold object that later pulses quietly across space. It is a compact furnace of dense matter, still settling after the core has fallen inward and stopped. Neutrinos carry energy away from its interior. Radiation leaves from its outer layers. The star begins its long cooling almost as soon as it begins its life. Cooling sounds simple only from a distance. A warm object loses heat. A hot surface fades. But inside a neutron star, heat is not stored in ordinary matter, and it does not escape through ordinary layers. The core is dense with particles whose reactions are controlled by pressure, degeneracy, nuclear forces, and possible paired states. The crust acts as a blanket, a conductor, a storage layer, and sometimes a delay. The surface glow is the final signal from a long path outward. In the youngest neutron stars, neutrinos dominate the loss of energy. They are light, nearly ghost-like particles that can leave dense regions more easily than photons. Though even they interact under the most conditions, a newborn neutron star can pour away much of its early heat through neutrino emission from the core. Photons from the surface matter too. But in the first long stage of cooling, the deeper escape route belongs mainly to neutrinos. This makes the cooling star a hidden test of composition. Different particles allow different neutrino reactions. Some channels are slow. They remove energy steadily, letting the star remain warmer for longer. Other channels are much faster, draining heat from the core with far greater efficiency. Whether the fast channels can operate depends on the mixture of neutrons, protons, electrons, muons, and any more unusual particles that may exist at depth. The surface temperature becomes a clue to what the core permits. One important family of reactions is often discussed through the Urca processes. The modified Urca process is slower because an additional particle is needed to carry away momentum and allow the reaction to proceed in dense matter. The direct Urca process is much faster, but it can occur only if the particle fractions in the core meet the right conditions, especially if there are enough protons. A star that cools unusually quickly may be allowing a fast neutrino channel deep inside. The cold surface then points back to a hidden reaction. This is not a simple thermometer lowered into the core. The signal must be interpreted through many layers. A neutron star's measured temperature depends on distance, atmosphere composition, magnetic field, surface hotspots, and the age of the object. The crust may delay the heat from below. The surface may be covered by light elements that let heat escape differently from heavier material. A magnetic field can guide heat unevenly, making one region warmer than another. Still, the cooling curve is not empty. It records which interiors remain possible. A cooling curve is a history of fading heat. It compares the temperature of neutron stars with their ages, placing each object along a long decline from birth toward darkness. Some stars fall where ordinary slow cooling models expect them. Others appear too cold or too warm for simple assumptions. Each difference forces a return to the core. The star is not giving a full confession. It is removing certain answers. Superfluidity changes the story in a quiet way. If neutrons in the core pair up, they enter a superfluid state. If protons pair, they may form a superconducting state. Pairing can sustain neutrino reactions because paired particles are harder to excite. At the same time, when pairs first form or break, they can create their own neutrino emission. This means that the cooling behavior may carry the timing of a phase change inside the core. A surface temperature measured today may preserve the echo of particles pairing deep below. The crust has its own cooling language. In some binary systems, matter from a companion star falls onto the neutron star and heats the crust during an outburst. When the outburst ends, the crust begins to cool back toward the temperature of the core. X-ray telescopes can watch the fading light over months or years. The shape of that decline reveals how heat moves through the crust, how conductive the layers are, and whether parts of the crust contain impurities or unusual structures. This kind of crust cooling is slower and more local than the long cooling of the whole star, but it is valuable because it gives a closer view of the outer layers. The crust is heated, then allowed to relax. The surface brightness falls in a measured way. From that fall, astronomers infer the thermal conductivity of dense matter. Nuclear pasta may slow heat flow near the base of the crust. Superfluid neutrons may alter heat storage. The fading glow becomes a map drawn without opening the star. Young isolated neutron stars offer another path. Their surfaces glow in thermal shrays as leftover heat escapes. Some are found in supernova remnants, where the expanding gas gives an estimate of age. If the remnant is young and the neutron star is already quite cool, the interior may be losing heat faster than expected. If it remains warmer, fast cooling may be absent or suppressed. Both outcomes matter. Heat that remains and heat that vanishes are both messages. The central compact object in the Cassiopeia, a supernova remnant, has often been studied in this way. Its age is only a few centuries, and its thermal emission gives a rare chance to watch a young neutron star early in its cooling life. Reports of temperature decline have led to discussions about neutron superfluidity and enhanced neutrino emission, though measurement and interpretation remain difficult. The value of the object is not that it gives one final answer. It shows how a small change in surface temperatures can point toward particle behavior inside the core. Cooling can also constrain exotic matter. Hyperons, quark matter, or other dense phases may open additional neutrino channels, or change the heat capacity of the core. If such matter causes cooling that is much faster than observed, the model becomes less plausible for that star. If it suppresses cooling too much, it faces another problem. Every proposed ingredient has to pass through the thermal record. The star asks not only whether a particle can exist at high density, but whether its presence leaves a temperature history that matches the sky. There is a softness in this kind of evidence. It does not arrive as a burst or a sharp timing glitch. It arrives as a surface becoming slightly dimmer, as X-ray counts gathered over years, as a temperature estimate refined through atmosphere models. The interior speaks by losing warmth. The deepest matter is read through the way it lets energy leave. That slowness suits the subject. A neutron star cools across ages far longer than a human life. Its early heat fades first through neutrinos, then more visibly through photons. Its crust adjusts after outbursts. Its core may cross pairing thresholds. Its surface may show only a small patch of what is happening below. Yet each faint thermal signal touches the same buried question. Which particles are present? And how do they carry energy away? The cooling star therefore belongs beside mass and radius as a guide to the core. Mass tells whether matter can support weight. Radius tells how much the star has yielded to gravity. Cooling tells how the hidden particles move, pair, react, and release energy. It is less direct than weighing a pulsar, but it reaches into a different part of the physics. It follows heat instead of shape. A surface that appears merely dim may be one of the clearest remaining witnesses. It has been altered by atmosphere, curved spacetime, magnetic fields, and the long delay of heat, crossing dense layers still. It carries information. The photons that finally escape are the last step in a chain that began deep inside the star, where neutrinos left the core and particles settled into the forms allowed by pressure. The remnant cools, and the cooling is not silence. It is a slow report from matter that cannot be touched. Some interiors fade too quickly in theory and are removed. Others stay too warm and become doubtful. The allowed core narrows. Beneath the surface, the star keeps losing the heat of its birth, and in that loss, the hidden matter leaves another trace. Two neutron stars can spend ages circling one another in the dark before the final test begins. Their orbit shrinks slowly, as gravitational waves carry energy away from the system. Each star remains compact, dense, and almost impossible by ordinary standards. Yet, together they become something even more severe. They are not only objects moving through space. They are two bodies of dense matter using their last orbits to reveal how strongly they can resist being pulled out of shape. As the stars spiral closer, each one raises a tide in the other. This tide is not like an ocean tide on a planet. There is no sea rising under a moon. The entire star is being distorted by gravity, its dense matter stretched slightly toward its companion. The amount of distortion is called tidal deformability, and it depends on the equation of state. A larger and stiffer star tends to deform more than a smaller, more compact one. A softer star keeps its mass packed tighter and leaves a different imprint on the wave. The signal leaves before the stars touch. Gravitational waves carry the motion of the orbit outward across space, preserving tiny changes in the rhythm of the inspiral. Detectors on Earth do not see the stars directly. They measure minute changes in distance, as space-time itself is stretched and squeezed by the passing wave. From that faint pattern, astronomers infer masses, orbital motion, and the deformability of matter that no laboratory can hold. This makes a merger one of the cleanest pressure tests in nature. A cold, isolated neutron star reveals itself through pulses, heat, radius, and mass. A merging pair adds another method. It asks the stars to answer gravity dynamically. The matter is not only supporting a surface, it is being pulled, heated, crushed, and finally joined to another body of the same kind. The equation of state is no longer only a quiet rule inside one remnant. It becomes part of a collision. When the surfaces meet, the distinction between the two stars disappears. Dense matter shears, shocks, and compresses. Some neutron-rich material is flung outward into space. Some forms a hot disk around the central remnant. Some falls into the merged core, adding mass to a body that may already be beyond what a cold, non-rotating neutron star can support. The remnant exists, if it exists at all, because extra support is temporarily available. Rotation matters here. A neutron star spinning rapidly can support slightly more mass than the same star without rotation. In a merger remnant, rotation may be even more complicated, with inner and outer regions turning at different rates. Heat also contributes for a time. Thermal pressure, turbulence, and magnetic fields may help hold the object open after the collision, but temporary support is not the same as permanent survival. As the remnant cools and loses angular momentum, the hidden boundary begins to approach. That boundary is known as the Tolman-Oppenheimer-Volkoff limit. It is the maximum mass of a cold, non-rotating neutron star for a given equation of state. The exact value is not fixed because the pressure of dense matter is not yet fully known. If the equation of state is soft, the limit is lower. If it is stiff, the limit is higher. Heavy pulsars already show that the limit must be above 2 solar masses. Merger data and radius measurements prevent it from being raised without restraint. The limit is not a wall that glows. It is written into pressure. A neutron star below it can keep a surface. A star above it, without enough rotation or heat to delay collapse, cannot remain a neutron star in the ordinary sense. Gravity wins the final part of the contest. The surface falls inward. An event horizon forms. The object becomes a black hole. A merger may take several paths toward or away from that ending. If the total mass is far too high, collapse can happen almost immediately. If the mass is only somewhat above the non-rotating limit, the remnant may live briefly as a hypermassive neutron star before losing support and collapsing. If the mass remains below the true stable limit, after heat and rotation fade, the object may survive as a massive neutron star. Each path leaves different traces in gravitational waves, gamma rays, kilonova light, and later X-ray or radio emission. The first observed neutron star merger, through gravitational waves and light, showed why this kind of event changes the field. The waves carried the final motion of the dense stars. A short gamma-ray burst followed from the same region of the sky. Optical and infrared light rose and faded as neutron-rich debris made heavy elements through rapid capture of neutrons. The event became a multi-messenger signal, with each messenger carrying a different part of the same story. The kilonova light is especially important because it shows that some matter escapes the merger instead of disappearing into the remnant. In that ejected material, neutrons can be captured rapidly by atomic nuclei, building heavy elements such as gold, platinum, and lanthanides. The glow changes color as the debris expands and cools. Dense matter that once belonged to 2 dead stellar cores becomes part of the chemical future of space. The central remnant is harder to read. It may collapse quickly, leaving only indirect signs of its brief life. It may survive long enough to feed energy into the surrounding material. It may leave a disk that powers further emission. The timing of collapse matters because it points back to the maximum mass and the equation of state. A prompt collapse suggests that support failed quickly. A longer-lived remnant suggests that dense matter, rotation, or heat held gravity back for a time. Future gravitational wave detectors may hear the post-merger remnant more clearly. After the stars collide, the central object may oscillate at frequencies related to its radius, mass, and internal pressure. Those vibrations would be difficult to detect with current sensitivity, but they are among the most valuable missing signals. They would come from matter at densities and temperatures beyond those of ordinary pulsars, ringing briefly before settling or disappearing. There is also the possibility of a phase transition during the merger. Matter, compressed beyond the usual core density, might enter a quark phase, or another state not present in lighter stars. If that happens, the gravitational wave pattern, collapse time, or ejecta properties could shift. The signal would not label the phase by name. It would show a change in stiffness, compactness, or survival time. The interpretation would still require caution, but the merger would have forced matter into territory that isolated stars may never reach. This is the last test before darkness, because the outcome decides whether matter continues to communicate. A surviving neutron star keeps a surface. It can pulse, cool, flare, deform, and send clues through light and gravitational waves. A black hole has mass and spin, and its exterior gravity can be measured with great precision. But the material state that formed it becomes hidden behind the horizon. The collapse seals away the dense matter that astronomers had been trying to read. The threshold is therefore not only a physical limit, it is a limit of observation. On one side, the star still answers. On the other, the answer is mostly gone. Merger. Remnants are valuable because they hover near that boundary, sometimes for milliseconds, sometimes longer, allowing the universe to test support mechanisms in real time. Neutron degeneracy, nuclear repulsion, thermal pressure, rotation, magnetic fields, and possible exotic phases all face the same demand. Hold the surface or lose it. The journey inward began with a visible boundary on a dead star. It passed through crust, neutron drip, pasta, core pressure, heavy pulsars, possible exotic matter, and cooling surfaces. The merger gathers all of those questions and asks them at once. How stiff is the matter? How much mass can it hold? How much can it deform? How long can it remain a star before the horizon closes? The answer is still incomplete, but it is no longer vague. It is being narrowed by every pulse, every X-ray cooling curve, every heavy neutron star, and every gravitational wave event. A neutron star remains one of the few places where quantum matter and strong gravity meet without immediate silence. It is almost a black hole, but not quite. It is almost unknowable, but not quite. Its final test comes when another neutron star draws near, and for a short time, dense matter speaks through the trembling of space-time itself. The journey does not need to fall immediately into quiet. After the merger, there is still a little more distance to travel before the final return. Not deeper into the star now, and not outward into empty space alone, but through the instruments and ideas that keep trying to read what the star cannot show directly. A neutron star hides its center better than almost any object that still has a surface. Yet it keeps leaving marks in the world around it. Those marks arrive in different forms. A radio pulse repeats with patient accuracy. Then arrives a fraction of a second earlier or later, because the star has moved with a companion. An X-ray pulse rises and falls, as a hot region turns across a surface where gravity bends the light. A cooling curve slopes downward across years, carrying the thermal memory of dense matter. A gravitational wave stretches an interferometer by less than the width of a particle. And in that faint stretching, two stellar cores speak about their own deformability. None of these signals alone opens the star. Together, they begin to surround the hidden core from all sides. The work is slow because each messenger has its own veil. Radio timing can measure mass with great precision in some systems, but mass alone does not reveal composition. X-ray modeling can estimate radius, but the answer depends on atmosphere, hotspot shape, magnetic field, and distance. Cooling can suggest which neutrino reactions are active, but age and surface composition can blur the reading. Gravitational waves can restrict tidal deformability, yet the signal often ends before the post-merger remnant can be heard clearly. Every method gives a line through the darkness, not a full picture. Still, a line can matter. The strongest progress comes when the lines cross. A heavy pulsar removes equations of state that are too soft. A gravitational wave event removes equations that make stars too large. X-ray pulse profiles restrict the allowed radius. Cooling observations reject interiors that lose heat too quickly or too slowly. Laboratory nuclear experiments narrow the behavior of neutron-rich matter at lower densities. The star is hidden, but the space of possible answers becomes smaller. This narrowing has a calm beauty of its own. It is not a single discovery that closes the subject. It is a gradual tightening, almost like focus being adjusted on something too far away to see directly. The image never becomes simple. It becomes less blurred. A model that once seemed possible is set aside because it cannot support a heavy star. Another fails because it makes ordinary neutron stars too broad. A third cools too quickly. A fourth cannot match the shape of a merger signal. The surviving models stand in a narrower corridor, pressed from every direction by evidence. In that corridor, the core remains uncertain. It may be mostly neutrons and protons, with electrons and muons keeping the charge balanced. It may contain paired neutrons, flowing as a superfluid, and protons in superconducting states that alter magnetic behavior. It may hide a phase transition only in the heaviest stars. It may allow quarks to appear at depths, reached only near the final edge of stability. It may include hyperons, whose interactions are strong enough not to weaken the star beyond survival. Each option remains under pressure from the same measurements. The future of the subject depends on hearing more clearly. New X-ray observatories may measure thermal emission and pulse profiles with greater detail, giving tighter estimates of mass and radius. More sensitive radio timing may weigh additional pulsars and follow glitches with finer precision. The next generations of gravitational wave detectors may catch many more neutron star mergers, and perhaps hear the short, high frequency ringing after the stars collide. That post-merger sound, if measured well, could become one of the sharpest probes of matter above nuclear density. The laboratory contributes from the opposite direction. On Earth, no machine can hold a neutron star core in a container. Heavy ion collisions can create dense nuclear matter for a moment, hot and expanding almost as soon as it forms. Experiments with neutron-rich nuclei can test how matter behaves when the balance between protons and neutrons shifts far from stability. Measurements of neutron skins in heavy atoms can help constrain the symmetry energy, the part of nuclear physics that affects how costly it is to make matter more neutron-rich. These are not neutron stars. They are nearby footholds. The bridge between laboratory and sky is theory. Equations connect the short-lived collisions on Earth with the long-lived compression inside stars. Simulations follow supernova cores, cooling crusts, vortex motion, magnetic fields, and merging remnants. Some calculations begin with nuclear forces measured in ordinary nuclei and try to extend them into the denser unknown. Others test what happens if new particles appear. The star keeps the final authority. A theory may be elegant, but it must still hold up the observed mass. There is a useful humility in that. Neutron stars do not allow dense matter physics to remain only a matter of preference. The sky contains objects that weigh more than 2 suns and still have surfaces. It contains mergers that do not deform without limit. It contains young remnants whose temperatures follow real histories. It contains pulsars whose timing carries the memory of internal motion. Every proposed interior must live in the same universe as those facts. The crust continues to play its quieter role in this narrowing. It is easy to think of the core as the whole mystery, and the crust as only the shell above it. The journey inward has shown otherwise. The crust stores heat, filters signals, anchors magnetic fields, and may take part in glitches. The inner crust may contain nuclear pasta, and that pasta may affect thermal relaxation, neutrino scattering, and the strength of the star's outer layers. If the surface is misread, the core may be misread too. The outer layers are not distractions from the interior. They are the path by which the interior becomes visible. Even the atmosphere matters. A thin covering of hydrogen can make a star appear different from a heavier element atmosphere under the same gravity. Magnetic fields can alter the way radiation leaves the surface. Hot spots may not be round. They may be stretched, offset, or shaped by field geometry. The light that reaches an X-ray detector is therefore a layered message. It has passed from core to crust, through atmosphere, around curved space-time, and across interstellar distance, before being counted as a photon in an instrument. The same layered message appears in time. A pulsar is not simply a rotating lamp. Its long-term spin-down reflects magnetic braking. Its sudden glitches may reflect superfluid motion beneath the crust. Its companion orbit can reveal mass. Its pulse shape can change if the magnetosphere shifts. A single neutron star can be clock, laboratory, and gravitational test at once, but only if the signal is read patiently and without asking it to say more than it can. There is another reason the final answer may be slow to arrive. Neutron stars are not all identical. Their masses differ. Their magnetic fields differ. Some are young and hot. Some are old and cold. Some accrete matter from companions. Some sit alone in the dark. Some spin hundreds of times per second. Some flare as magnetars. A low-mass neutron star may never reach the central density needed for an exotic phase. A heavy one may. A merger remnant may pass through states that no isolated star ever touches. The interior may not have one universal form. This possibility makes the subject richer and more difficult. The answer to what lies inside a neutron star may depend on which neutron star is being asked. Some cores may remain nucleonic. Some may contain hyperons, or quark matter, only in their deepest centers. Some may briefly become hybrid objects after mergers, before collapse. The category neutron star may cover several internal arrangements, all sharing a surface, gravity, and dense matter, but differing in the last details of the core. That is why the coming years matter. More objects give more pressure points. A very heavy pulsar found with a large radius would strengthen the demand for stiffness at high density. A merger with a clear post-merger signal could show how hot dense matter behaves immediately after collision. A young star cooling faster than expected could point toward rapid neutrino emission or pairing transitions. A persistent gravitational wave from a spinning neutron star would reveal a stable asymmetry and perhaps the strength of the crust. Each new observation would remove a little more darkness. The deepest lesson remains simple in shape. Matter changes when pressed. At first it changes gently, becoming plasma inside a living star. Then it changes by quantum exclusion, allowing a white dwarf to survive without fusion. Then it changes by electron capture and neutron degeneracy, making a neutron star from a failed massive core. Then it changes again in the crust, where nuclei grow neutron-rich, neutrons drip out, and nuclear clusters may stretch into pasta. In the core, it may change into a fluid with paired particles, or into phases not yet confirmed. The whole journey is one long answer to gravity. Gravity itself is the constant presence. It does not rush. It does not need complexity. It simply pulls. The complexity belongs to matter, which keeps finding different ways to resist until one of them fails. In stars, resistance appears as heat. In white dwarfs, as electron degeneracy. In neutron stars, as neutron-rich matter and nuclear force. Near the last limit, perhaps as quarks, perhaps as stronger interactions, perhaps as rotation and heat that delay the final fall. The forms differ, but the contest remains the same. A neutron star is valuable because it has not yet become silent. It is close enough to a black hole to test gravity strongly, yet still made of matter that can leave signals behind. Its surface is harsh, but it exists. Its light is bent, but it escapes. Its core is hidden, but its pressure shapes the radius. Its crust is buried, but its heat and stress reach the surface. Its mergers are violent, but their waves travel outward cleanly. It stands at the last place where dense matter can still be studied before the horizon removes the evidence. So, the final pause before the ending is not a summary of facts. It is a widening of the view. The star that began as a point of impossible density becomes part of a larger web. Observatories in orbit, radio dishes on Earth, interferometers listening for space-time, laboratories measuring unstable nuclei, and theorists trying to make one rule hold across all of it. The neutron star remains far away, but its meaning moves through all these places. The signals continue to arrive. A pulse, a faint ray glow, a cooling surface, a ripple from a collision long past. Each one is small compared with the object that made it, and yet each carries a trace of matter under pressure. The interior does not reveal itself all at once. It gives pieces, enough to keep the question alive, enough to make the darkness around the star feel less empty. Before the final quiet, the neutron star can be left at this threshold. A dead star that still has a face, a core that still resists, and a surface that still sends evidence outward. The universe has pressed matter almost to disappearance, but not entirely. Something remains there, holding shape against gravity, waiting for the next signal to cross the dark. The star remains far away now, small again against the dark, no longer a place to descend through, but a quiet point of pressure and light. Its surface is still there, curved under gravity, cooling slowly, sending faint traces outward through space. The journey has moved through its layers and beyond them, and now the motion can become slower. There is no need to hold every detail, the crust, the core, the pulses, the waves. and the hidden pressure can drift apart like distant stars returning to their places. What remains is the feeling of a boundary held in silence, a dead star that did not quite disappear, a small surface still answering the pull beneath it. The darkness around it is wide and calm. Light leaves the star and travels on, weakened by distance, softened by time, carrying only what can escape. Somewhere far from the remnant, that light becomes a faint mark in an instrument, a small count, a pulse, a glow. The rest stays hidden inside the star, where matter keeps its final shape a little longer. Now the view can pull away. The neutron star becomes smaller. The nebula around it becomes mist. The galaxy becomes a pale river of stars. The questions remain, but they no longer need to be solved tonight. They can stay where they are, suspended in the quiet between gravity and matter. The room is still here. The air is still here. The body can rest while the mind lets the last image fade. A compact star in deep space, holding its surface against the dark, almost gone, but not gone yet.